Right, so today's the third section, chapter 11. We're trying to learn how to check whether a series is convergent or not. We find out there's a very useful method to check that when the sequence is determined by a function. Okay, so let me our question is, we begin with the following question, and we will eventually to figure out how to do it. So, like this simple function, it's called a P series. Question is when it's convergent, when it's divergent, right? And let's assume that P is positive, right? So I know the nth term approaches 0. Okay, note that nth term equals 0, but does not mean if the series convergent. Okay, it's possible for certain value p that it is divergent to the infinity, but the partial sum clearly increases. Okay, so there's only two possibilities if you let sk to be the partial sum, n from 1 to, I cannot group them together. So this is an increasing, right? That's only two possibilities. It has upper bound or no upper bound. If it has upper bound, then this convergent to a finite number. If it is unbounded, then it's divergent to the infinity. So you only have two cases, or positive infinity, or right, or a finite number. Right? The question is, for what the value of p? Yeah, it is. Yeah, for what the value of p? So we don't know yet, right? We're going to figure it out later. Okay. So we consider the special sequence, right? Okay. So we let fx be a continuous positive and decreasing function. Okay. On the interval, let's say from a to infinity, it's not necessarily from 1 or from 0. Okay. Then we consider this series. Yeah, let's assume that it's from capital N, okay? That's enough, yeah. So then N is greater than or equal to capital N. But I want to use a function to check whether the series is convergent or not, okay? So what I know is, yeah, let's before I state the theorem, let's figure out what's going on here. It's n to the n plus 1 integrate. Okay. So what do you get? The function has an upper bound. Okay. Before I should say, yeah, before the integrate, it's going to be n plus 1 f of n plus n, right? Decreasing. And this is but this is a constant, so just equal to f of n. That's equal to f n plus 1. So in other words, the integral of the function is between those two values, great. Okay. So now you're going to add them together. Okay, you add them together, sigma n from capital N to k, okay? A n less than. If we add them together, you have you have many integrals, but because the integrals can combine into one single integral, that's great. Okay. So now the convergence of the integral, improper integral, gives you the convergence of the series. So what you can get is is less than or equal to if you let k goes to infinity. Okay. So great. So that means if the series is convergent, then the integral is convergent, because if this is a finite, the integral is finite. Okay. If the integral is finite, you can make the other one finite. Okay. So this concludes that if and only if is finite. Okay. Convergent or finite. Same. All right. So it's the same. Now we can also probably can figure it out. You can get the estimate. Okay. You can estimate it from I think we can even estimate the using the integral estimate it. So this is nothing but sigma n from capital N. I think you have to minus the first term. Okay? Yeah, it's labeled, it's from capital N plus 1, from capital N plus 1. So you can also get another estimate. You move this to the right hand side. Plus A capital N. But this is always greater than or equal to. Yeah, you can move the infinite series in the middle of them. So now if the integral is finite, convergent, then you can even estimate the value for this infinite series. Right? It's between those two. So that's, if you just want to talk about convergence, then you don't need to worry about that. If you want to estimate the value, it's between those two bounds. Okay. The integral of the function, and also you need the first term. Okay, let's look at the following problem. Okay, P is positive. Okay, let's see what happens. First of all, when P is positive, so this n, okay, this is going to be f of n. What is f of x? F of x is going to be this. It's going to be this function. All right. So clearly, it is continuous, positive, decreasing on the interval from 1 to infinity. Okay, it has three properties. So you can use this integral, use this function to check the convergence of the series. Okay. So we know that, so we know that by the above inequality, n start from 1 and our np is less than or equal to from 1 to infinity, and plus the first term, which is 1, and greater than or equal to 1 to infinity. Okay, so the convergence really depends on the integral, right? Yeah, if the integral is finite, then the series is finite. and you can evaluate the value, estimate it. If the sequence, if the series is finite, the integral also finite. It pushes that. Anyway, you have this bound. All right, so let's figure it out. Okay, so let's take a look at this integral, finite interval. All right, so the antiderivative is 1 minus p as 1 minus p, and evaluate the two endpoints. So you will get minus of this. Okay, when this one has a limit, finite limit, I think when p is less than 1. When p is greater than 1, sorry, when p is greater than 1, this goes to the dominant. So it approaches, right, if p is greater than 1. If p is greater than 1, then this approaches 0. So you can write as negative 1 over 1 minus p, which is 1 over p minus 1, it's positive number, right? Now, if p is less than 1, greater than 0, b is to the positive power, so it's going to be positive infinity. Okay? What happens when p equals negative, p is going to be 1? If p is going to be 1, you treat it slightly different. You have to use a natural log. Okay? And that is going to be natural log of x. This clearly approaches infinity as b approaches infinity. Okay? All right. So now what? We get to the following conclusion, right? If p is greater than 1, you get this. Otherwise, you get infinity. P is less than or equal to greater than 0. Okay? Okay. So this also implies this power series. No, this series, P series here. This P series is finite. Yeah, it's going to be convergent if P is greater than 1. Divergent if P is less than or equal to greater than 0. Right? Not only that, you can even estimate the value. It's less than or equal to the integral of this plus the first term. Integral of this is going to be p minus 1 plus 1. Okay, in the case p is greater than 1, greater than or equal to. You can even estimate the value. That's great. Okay, otherwise, how do you know that, right? So for example, like when p equals 2. When p equals 2, you have 1 over 1 square plus 2 square plus 1 over 3 square plus 1 over 4 square and so on. Okay, this series is less than or equal to p equals 2, so it's 1 over 2 minus 1 is 1, so it's less than or equal to 2, greater than or equal to 1. Of course, greater than or equal to 1 is obvious, but less than or equal to 2 is not obvious. Not even you can get that. Okay, so this is called the P series test. Next time we're going to use that P series. Okay, sometimes we will change that series to that. So this is going to be a useful theorem. Yeah, this is going to be useful theorem. So let's call it, yeah. Yeah, we're going to use this in the future. Okay, so when P is greater than 1, means this sequence decays very fast. So every time we add a tiny bit small number, that number is too small. decays too quick, so it does not contribute too much to the sum of the infinite terms. So eventually, it will not increase, go to infinity. It will not go to infinity. Okay. So this is an example. Another one is related to that. Let's look at this series. So yeah, in particular, so let's look at it. In particular, this harmonic series is divergent. This is divergent. It's called harmonic series. When p equals 1, that's a special case. That's a special case. Okay, when p equals 1. Okay, and how about the next one? I know 1 over n is divergent, and the 1 over n squared is convergent. How about n to 1.1, right? So this is definitely also convergent, and by the integral test, okay, this is a convergent. Okay, since p is 1.1 is greater than 1. Okay, and you can estimate it using above formula. It's less than or equal to p minus 1 0.1 plus 1 greater than or equal to 0. Okay, so p minus 1 is 0.1. So that means it's between 10 and 11. It's pretty accurate, right? Yes. All right, so if the power is tiny bit larger than 1, it's convergent. How about this? N natural log of n. Because n is really compared, natural log of n compared to n is not on the same scale, okay? A decay scale, the growth scale, So natural log of n is smaller than n for any small positive. So smaller than, a to the n, okay? It's greater than 1, here action is greater than 0. So yes, it's greater than 1, but it goes to infinity, but not that fast. But when you put together, and I have to start from 2 because natural log of 1 is 0. Yeah, n equals 2. Okay, so is it convergent or not? Is it convergent or not? Can you think about this? Yeah. So you look at the corresponding function. Okay, f of x is equal to x natural log of x. On the interval from 2 to infinity, I think it's continuous. Positive, yes, and the decay decreasing. Clear. Of course, decreasing to 0. Let's look at the integral of this function. I think I can evaluate. Okay. It is a substitution. Okay. So, so what is that? Right? That is going to be the limit as b approaches infinity. Okay. So the antiderivative of this, it's not easy to find out, but you have to use substitution. Let u to be natural log of x. When you use this substitution, du equals 1 over x dx, right? But the intervals also be changed. It's natural log of 2, natural log of b. And 1 over u is here is u, okay? And then that's du. Yeah, dx, du is, yeah, the dx over x is du. And this will be natural log of u again. So the answer will be natural log of b minus natural log of 2. Clearly, it approaches positive infinity. Okay, as b approaches infinity. So it's divergent, right? So it's divergent means this is a divergent. That is going to be, yeah. So that implies divergent. Now this example shows maybe if you increase the power of natural log of n, maybe it's convergent. Okay, you can. So my question is, determine the value p so that it's convergent. When it's divergent. Okay. Yeah, think about this. So here's p is greater than 0. Okay, if p is it's goes to the top, definitely it's divergent. I will show you later. Okay, if p is 0, then it's natural log will disappear. So think about, give you a minute to think about how to check whether this, for what value p it's convergent. Okay. So for the same reason, you do exactly the same select both. Okay. So the n is going to be n natural log of n. So that is going to be f of n. Okay. So here's a function. Instead to say this is decreasing positive, okay, and the continuous. So you can apply the same, okay? So then you look at the integral of this function. So that is going to be right? Then you use the substitution. Okay, du equals 1 over x dx. So this integral becomes natural log of 2, natural log of b, and here's u to the p du. Okay. So now, this is the integral we saw before, right? So we can find the when it's convergent, when p is greater than 1. When p is greater than 1, this is going to be 1 over p minus 1. Not 1 over p actually. Actually, it's going to be let's evaluate. Okay, but when p is greater than 1, so the antiderivative will be 1 minus 1 minus, right? Okay, so you will get okay. So the limit, this goes to the this limit when p is greater than 1. Okay, this is going to be p is greater than 1. Otherwise it's positive infinity. If p is less than 1. Okay. Yeah, I include in the case when p equals 1. Yeah, the antiderivative is not different if you use p equals 1. Okay. So I just forget this. Yeah. When p equals 1 is special case. Clear. It's divergent. So so we see that it's similar to the P series, okay? But you can also get an estimate of this. So the integral from 2 to positive infinity and x natural of x to the p dx is going to be this. If p is greater than 1, otherwise it's going to be divergent. If p is less than or equal to 0, okay? Yeah. Then you can estimate even the PC as a series. The value can be controlled by this integral, okay, when p is greater than 1. All right, let's take a look at some example from the book. Determine whether the series is convergent and divergent. And let's consider this. Well, this is not exactly P series, but I'm pretty sure it's convergent because it's n squared, right? But we haven't learned the so-called comparison theorem, so we cannot tell whether it's, yeah. But I guess it's convergent, okay? But I'm not going to use a comparison theorem to show that. Okay, if you want to use a comparison theorem, it's obvious. The reason is 1 over n squared plus 1 is less than or 1 over squared, right? Yeah. Okay. So you put a sigma, right? And I know this is a finite, and this is greater than 0, right? This is a finite. So that clearly indicates this is convergent. Okay, so that implies, but this is a method that we are going to learn late. Yeah, this is convergent. But there's no, yeah, you can estimate using the one on the right-hand side. But I'm not going to do this way. This, but I still use the integral. Okay, so this is going to be f of n. So where f of x is going to be 1 over x squared plus 1. So 1 over x squared plus 1, check the condition required. It's the case, positive. Okay. All right. So this is a, yeah, the 1 over x squared plus 1. So you just need to look at the integral. So from 1 to infinity. Okay. If you want to save time, just find the antiderivative of this. So it's going to be arctangent x evaluated to endpoint. So this means you take the limit, okay? The arctangent, the derivative arctangent is going to be 1 over x squared plus 1. So arctangent, when x goes to infinity, arctangent infinity is pi over 2. Yes, pi over 2, right? Then arctangent 1 is pi over 4. So it's pi over 4. Okay? Okay, so we conclude that this is going to be convergent. Yeah, it's finite. Not only that, you can estimate. Remember, we said that this is going to be greater than or equal to the integral of the function, right? Integral of the function, right? And this is going to be integral function plus the first term. When n equals 1, it's going to be 1 over 2. Yeah. Right, so this can be pi over 4. Pi over 4. We get pretty good estimate. So the integral test not only give you the information about convergence or divergence, when it's convergent, you can also get an estimate sometimes. Okay. Okay, the next one. This is a n square natural log n. Okay, is it going to be convergent or not? I think it's convergent. Why it's convergent? This is the way I'm analyzing. Okay, when you give a series, you know, you can separate like that, 3 over 2, natural log of n to the 3 over 1/2, okay? But this number is getting smaller and smaller, okay? This actually goes to 0 because it's the denominator is a power function with positive power. The numerator is natural log of n. You can use a L'Hopital's rule to prove it, right? So this convergent is P series, P equals 3 over 2. So this is convergent, and you have some number, it's going to be very small, multiplied. Of course, the series is going to be convergent. Okay, that's the rough idea. But we're going to use the integral test to check this convergence. Okay, I know this is going to be convergent. Can you find it? So if you make every term smaller, of course it's going to find it, right? And you know that natural log of n to the 1/2 is going to be smaller than 1, greater than 0 for larger n. Maybe n greater than or equal to 4 is enough. Yeah, I just say n is greater than or equal to 4, it's already enough. Maybe not enough, 9, 10, some number, okay? Because natural log n grows slower than square n, okay? Okay. So combine this, we get some idea. This is going to be final. Okay, this is going to be final. That's just anything. But if you want later, you want to use a comparison test to check. Okay, right now we have to use the integral test. Natural log n squared equals f of n, and where f of x is natural log x squared. And now it's not clear. It's this on the 2 infinity. Okay, number 1 it's positive. Yeah, okay, positive. Continuous is obvious. I don't need information. Decreasing is not obvious. You have to check. Okay, this is okay, but that decreasing is not easy to see. How do you prove it's decreasing? Right. To prove a function is decreasing, the best efficient way in calculus is to find the derivative is negative. Change, show something is negative is easier than show something is decreasing. Okay, so you find the derivative. X to the fourth power. Natural log of x is 1 of x minus the derivative of the denominator. Okay? Yeah. So you simplify it. So you get x, right? Minus 2. When it's, wait a minute. Am I right? Hold on. I'm confused. The derivative of the numerator, okay, times x squared, denominator, minus the numerator times the derivative. I'm confused. Let's do that here, because this is going to be positive when x is large. Impossible. Yeah, the formula says f of g, right? It's in g squared, f of g minus f g prime. Okay? So f prime is 1 of x times g, that is x squared, minus natural log x times g prime x. So I can, x squared over x is just x. Oh, I have a, yes, it's not x. Yes, there's x here. Okay. So now, yeah, how do you see it's negative? You take x out, right? So can divide that. 1 minus 2 natural log x. When it's negative, when x is sufficient large. Okay? When natural log x greater than 1/2. Okay? When x is greater than e to the 1/2. Okay? E is 2.7. So this clearly for x greater than or equal to 3. Now, I don't know natural log of 2 is greater than 1/2 already, but the natural log of 3 is greater than 1/2. Okay? And after that. Okay? That's good enough. Okay? So that means f of x decreasing on this interval. Okay? Then you can compare it with the integral. Integral, let's use, doesn't matter from where to where, can from 3, can from 2. It's, yeah, let's look at this integral. Natural log of x, x squared dx, okay? Let's look at this integral. How do you evaluate this integral? Can you do that? You have to find the entire derivative. You have to get rid of natural log of x. You can try use substitution. Let u to be natural log x, but you are not able to simplify it. Okay, so you have to go to this natural log x. Okay, so my idea is to use an integral by the part. Okay, this is my dv. When I switch it, right, this is u. Okay, v is going to be x to the negative 1, right? When you differentiate, you get x to the negative 2. Yeah, dv equals x to the negative 2 dx. Okay, so it's uv, right? uv minus v du. So u is going to be natural log x, v is negative x to negative 1, and minus x negative to negative, right? du is going to be 1 over x dx. Oops. So it's going to be negative plus, and here's x negative 2 dx. So the entire derivative of that will be negative x to the negative 1 plus constant. So when you differentiate, you should be able to get yeah, cancel out, you should get an origin function. So this is the entire derivative. All right, so once you get the entire derivative, then you will get negative natural log of x plus 1 over x, right? Yes. So evaluate the two endpoints. Okay. So clearly this convergent to the first term convergent to 0. So this convergent to 1 plus natural log of 2 over 2 as b goes to infinity. All right, so that should be convergent. All right, so we get this answer. Yeah, so natural log of b over b goes to 0, okay, as b goes to infinity. That's a simple fact. It's obvious. So use that to find the limit. So this implies this integral is finite. So this implies sigma n from 2 n square natural log of n2 is convergent by the integral test. Okay, you have to set that by which test? By the integral test. All right, so there was a famous guy called Euler, okay? He became blind when age 40, but he published so many papers. So in the mankind history, in human history, there are very few genius guys, and he's among them. Okay? We don't know why they become so genius, like Newton and Euler. Okay. So this is he actually proved that it's when n equals, you cannot use the integral, we can only estimate right now. Okay, and then he also did this when it becomes fourth, it's going to be pi to the fourth power 90. Okay, So at least it's convergent, and he even find out that the infinite series, okay, convergent to some very special number. It depends on pi, but at the very beginning, it does not look at pi, right? That's pi is not there. It's harder to, but this is important formula because you can use that to estimate pi square of 6 by take sufficient many terms, add them together. Okay, computer can do very fast. Okay, but 300 or 400 years ago, how did he get that? It's smarter than us, right? Right now, we're struggling with calculus course. But yeah, it's harder to tell. Okay. So the question is mathematics useful or when it's useful? I think when he did this part, he probably did not know it's useful or not, but at least it's a proof there are some animals, creatures on the earth, their intelligence reached to that level. Okay, it's better than monkeys. So that they figured out what is called pi, and they even know this power series. Okay, so that's I can tell. But you're surprised that those kind of mathematics is really useful if you're looking for a job at National Security Agency, and then they will ask you, do you have a math background? How much you know about mathematics? Okay, that's the first. So the data and analysis, all kinds of things, you have to need the mathematics to work for that. Okay, we have an assistant professor. He left. I remember the next job he got is from National Security Agency. Yeah. Okay, he was here for a couple years. Okay. Yeah, that's sometimes the related mathematics, sometimes not exactly. And the people can make very stupid things. If you become an engineer someday, was a company, your job can even ruin the whole company. If like a Boeing right now, I think that they're going to be probably it's going to be big trouble. Because why? Because those chief active, general manager, also those engineers, okay, and that design the airplanes, they modify it, and without too much testing, then they just put, making thousands of airplanes, and now they can come back seamless. Okay, once the airplanes it's not easy to modify. They're trying to save money, save gasoline. They make the engine large, find a nice engine, great. They find out this engine too big, so put it in the same airplane. How do they do that? Then because they move the position of the engine. When they move the position of the engine, then they find out the airplane cannot fly naturally. So then they're asking the Indian guy to write a software for the airplane. When the software, so complicated software, right? You cannot rely on the software to do everything. Okay, but the software is not enough. You need a sensor to tell the software there's something wrong with that. But what happens when the sensor is broken? Then that's what happened. Okay, then the pilot cannot control the airplane. Last minute, it's nowhere can push the button. Somewhere disable the software and just control by themselves. That's what happened. The two airplanes crashed, and they did not get the manual. Even the pilot was not told. I was just shocking. That's so engineering. Yeah, it's very very important. Engineers in companies. Okay, then have to do the calculation. This requires mathematics too. The airflow, everything. It's very complicated called flow mechanics. The flow mechanics requires mathematics too. Okay, that's why they're all connected. Before do testing, you have to come to the computation, modeling. Yeah, simulation, we call it, yes. Okay. Oh, the things become more complicated. That's what Donald Trump was a little bit upset about that. You guys make the airplane so complicated. It's harder to handle it. All right. So let's do the next problem. All right. So let's look at this to check whether this is convergent or not, and to estimate if it's convergent. Okay, so right now we only have a limited methods, so we don't need to make a wise choice to which method we're going to use to check this convergence now. Later on, we're going to learn more methods. More method does not mean you can make you more smart. You have to be trained, okay? So you can choose the best one quickly. Otherwise you can make you more confused and which one is good. Then you use the wrong tool to solve the problem, okay? More methods good, but you have to be more trained, you have to be more practice. That's very similar to you know, to the job you're going to do in the future. You have so many equipment tools you can use. You don't know which one to grab, right? So right now we only learn integral test, so we can try and use that method, right, to answer the question. So here, f of x is going to x to the fourth plus 1. I want to check if this is a decreasing, convergent, decreasing positive. Positive continuous is obvious. Decreasing is not obvious, but it looks like decreasing because the denominator grows fast than the numerator when x greater than equal to 1. So all I have to do is to find the derivative. Okay? And here's x to the fourth power minus x times 4x2. Okay? So x to the fourth power plus 1 minus 4x to the fourth power. Great. So it's easy to see it's negative. Okay? So 1 minus 3x to the fourth. When it's negative, I think it's clearly it's negative if x is greater than or equal to 1. That's all I need, right? Why x greater than or equal to negative? Because 3, at least the value, x3x to the fourth power is 1. So it's negative 3. So it's negative. So negative means this decreasing and meets the requirement for the integral test. Then all you have to do is to look at this integral. Then what? I have trouble with this integral, right? Okay, so is this convergent or not? That comes to the knowledge. You have to use the knowledge from Math 163. Okay. So I have to find the antiderivative of this function. Then before I do that, I need I just use this. Okay, we need a substitution. That's why I don't want to fix. You let u to be, you have choices. X to the fourth power plus 1, x squared, right? I think x squared is the right choice based on my experience. Because I want to get x in the numerator, du equals 2x dx, right? This is great. So I get x to the fourth power is u squared plus 1, and here's 1/2 du. Okay. Then I got arctangent u plus constant. Then arctangent u becomes arctangent x squared plus constant. So the entire derivative is arctangent x squared. Okay. So now it's clear that okay. So the first, when you plug infinity for x, you get arctangent infinity. Infinity is going to be pi over 2. That's then arctangent 1 is pi over 4. So the answer will be pi over 8. Okay. So this is finite. Anyway, it's finite. So this implies n to the fourth power is finite. It's convergent. Not only convergent, you can estimate, okay? You can estimate it's between the integral pi over 8 plus the first term when n equals 1 is 1/2 greater than the integer. Okay, so it's pretty good estimate between those two numbers. Okay, it's integral plus the first term, and here's the left hand side just integral. So you can estimate. Okay, one more problem then later. All right, so this one, I still think it's convergent. The reason is this is the same as k e to the k squared. I think the denominator grows much faster than the numerator. And yeah, so it decays. Okay, clearly. So the question is, how do you prove it's convergent using the integral test? So here's f of x is going to be x e to the x squared, right? Right? The corresponding function. It's positive, it's continuous, but decreasing, you have to prove it. Yeah, this is another true function. So decreasing, you have to be careful when you differentiate. So it's 1 e to the x squared minus x. When you differentiate e to the x, I get 2x here, right? E to the x squared. So you take e to the x squared out, you get minus 2x squared e to the x squared. Okay? After simplifying, and clearly it's going to be negative. Oops, please go away. Okay. I don't know which one shows up. No? Oh, okay. So it's going to be negative if x is greater than or equal 1. So it's decreasing, no problem. So then then it's decreasing. Then you can use the integral test. So still a long way to go, right? It's going to be x e to the negative x dx. But this time you can use a substitution. You can use substitution. You can let u to be x squared. So du equals 2x dx. When x equals 1, use 1. When x equals infinity, use infinity. E to the negative u. And the x times dx is half of du. Okay. Then the antiderivative of negative, that's negative e to the negative u. It's from 1 to infinity. And I think it is going to be 1/2 e to the negative. Okay. So that's fine. Yeah, that's good enough. So then I get not only it's finite, I also get new dot. Okay. Then I get the integral. This is going to be yeah. Not only you can prove it's convergent, you can prove that you can estimate when k equals 1, it's going to be e, right? 1 over e. Okay, so it's very nice estimate. Yeah, it's a very nice estimate. So it's between 1/2, those two numbers. It's very close to, 1 over 2e. Right, so we